All right, hello everyone. Let's get started with day four. Day four of the Code Every Day, and today we're looking at day 13 of Advent of Code, 2024. So today is January 19th, 2025, Sunday at 5:14 p.m. All right, so let's look at this problem. There's a new arcade. Win prizes from a claw machine. So we're looking at claw contraption here. If two buttons labeled A and B, it costs 3 tokens to push A and 1 token to push B. You figure out that each machine's buttons are configured to move the claw a specific amount to the right and a specific amount forward. X and Y, okay? So we can never go left or backward, I guess. Each machine contains 1 prize. To win the prize, the claw must be positioned exactly above the prize on both axes. You wonder, what is the smallest number of tokens you would have to spend to win as many prizes as possible? You assemble a list of every machine's button behavior and prize location. Okay, for example, so if you press button A, you can move here, and if you press button B, you can move in those directions, and this would be the prize. Okay. The list describes the button configuration and prize location for 4 different claw machines. So just the first claw machine, so that's this one. Pushing the machine's A button would move the claw 94 units to the right and 34 up. Pushing the B, okay. So you'd have to get exactly there. Perfectly aligned. The cheapest way to win the prize is by pushing the A button 80 times and the B button 40 times. Is it also possible that it's not possible to reach the prize, or is every... doing this would cost... Okay, so this formula is important. So it's the number of times... Okay, yes, this looks like some sort of algebra here. Doing this would cost 80 times 3 tokens, because A requires 3 tokens for 1 press, right? Yeah, it costs 3 tokens to press A and 1 to press B. So you want to minimize the number of tokens, right? Where did it say that? Smallest number of tokens. Okay, so we want to minimize the number of tokens to get the prize. I wonder, do I have to do all 5, or do I pick only some of them? I'm guessing probably all 5. For the second and fourth, there is no combinations that will ever win a prize. But for the third claw machine, another example. So the most prizes you could win is 2. The minimum tokens you'd have to spend to win all 2 is 480. Okay, so if there's 4 here, you can only win the first and third. Okay, you estimate that each button would need to be pressed no more than 100 times to win the prize. Okay, so that's like a cap. So if we press either button, you estimate that each button would need to be pressed no more than 100 times. Okay, so you can maximum press each button 100 times, but people are not willing to do 101. Figure out how to win as many prizes as possible. What is the fewest tokens you would have to spend? So kind of what jumps out to me for this is you sort of just do a nested for loop. So you have, if you want to visualize this, so you have to reach, so you have like 94x, so every time you press X, plus 34y equals, So either way, so if you press A, it will give you, so if you press A, X goes up by 94 and Y goes up by 34. And if you press B, then X goes up by 22, and I'm just looking at the first example here, and Y goes up by 67. And then you want that to equal I'm wondering 8,400 and 5,400. So I'm wondering if we can write this somehow as like a system of equations. So we want, so X must equal 8,400, Y must equal 4,500, or sorry, 5,400. So obviously what I'm thinking, the simplest way to do it would just be for A in range 100, and then for B in range 100. And then this would give you every combination of pressing A and B. So it would give you, like, for instance, so if you press, like, let's say 75 times A and 15 times B, you could then calculate what your position is at this point, which is equal to, so your position can be defined as the number of times you pressed A. So it's X and Y, right? So your X is going to be the number of times you pressed A plus how much it goes up by. And this was also given in the problem too. This, and then your Y is the number of times you press, actually wait, plus, okay, so so your X position is 75. Okay, so this is kind of, so let's imagine I pressed A. So this is how many times you press A, and this is how many times you press B. Okay, so your position is not necessarily going to be lined up with that. Well, yeah. So this is the point 7515, and then using these two numbers, you can calculate some position equal to, so the X component of the coordinate is 75 times 94, and then plus 15 times this number here, 22. And your Y position is equal to the X component, or the A component, which is, so the Y component of the A button. So we press the A button 75 times, 22 plus, then we press the B button 15 times plus 67. So using these formulas, you can find position as a function of the number of times you press A and the number of times you press B. So you could just calculate all combinations of like all possible A and B button press combinations, which would be, so this is what, 10 to the 2 times 10 to the 2 is 10 to the 4. So that's 10,000. So that's fine. So you essentially do 10,000, and then you store, if my position There's also, you might be able to somehow use binary search somehow. So if my position, so let's just go over the brute force first. So if my position is equal to like prize position, then record how many tokens it take you. How many tokens? So you would say like tokens is equal to 3 times your A button presses plus 1 times your B button presses. And then if this is less than, and then obviously you just take the minimum. So you could say like tokens equals minimum between this and what you already had. So it'll update if it's lower. And then if you get through the whole loop without finding it, then obviously you can't reach it. So I'm wondering if you could do some sort of like modification or like 2D binary search for the position. So instead of doing every combination, you know that maybe you could binary search each component. So like if the X position is greater than where you need to be, then you can go half of the number of tokens. And then also, yeah, so we should just do it one case at a time. So it's really just a function of A and B. And you can I was gonna say you can do the components separately, but not really, because, well, can you? Well, maybe you can write this as, so you know that 94 times A plus 22 plus B must equal 8400. That's true. So the X components, it must equal 8400. So that's for X. Y would be 22A, or no, not 22. It would be 34 of A plus 67 of B equals 5400. And A, and then you know that 3A plus B equals tokens. So this system is solvable, I believe. Maybe. So you would have 94, 22, 8400. So if we write this as a linear system of vectors, then we know (94, 34) times some number A plus 22, 67 times some number B must equal 8400, 5400. So this is a linear combination of vectors. And then if you want to solve for this, I took linear algebra last semester, so maybe I can remember it. Do you just take the RREF of this? And that'll give you a solution? Hello? Alright, I'm back. So I decided I'm not going to do any linear algebra stuff, and I'm just going to try to do it with normal Python libraries. And I'll probably just do this algorithm, just ignore that, this thing that I was talking about, where I'm just going to loop through both, and then maybe somewhere I can find a binary search. I think I'm just going to start by doing the brute force algorithm first. Okay, so what I want to do essentially is open the file. So the data. So parse the data. So parse data, and the way I want it, the way I want the data is, I'll call it like maybe like AX increments, BX, or maybe like I could store them as tuples. So like A increment, and then it'll be the X jump and the Y jump. So for instance, 94 and 34, and then B increments would be 22 and 67. And let me just make sure it comes in like that. Okay. 22 and 67. And then also we want prize, target, which is same thing. So 8400 and 5400. So I'll basically just read it in as tuples of X and Y. Okay, and then I'll say for A in range. Let me write this a little lower in case I want to add something. I should have just moved it, but that's all right. We're here now. For A in range 100. For B in range 100. We want to check if the combination is valid. So check validity of the combination, and then update answer if necessary. And this will run 10,000 times, I believe, because that's 10 to the 2 times 10 to the 2, 10 to the 4. So 1, 2, 3, 10 times 2, 3, 4. Yeah, okay. Wait, is it 100,000 actually? 100 times 100. No, it's 10,000. It was 100 times 1,000 would be 100,000. So it's 10,000. So 1 times 10 to the second is how you can write 100 times 1 times 10 to the second is 10 to the fourth, and 10 to the fourth is 10,000, because you can write that as 10 times 1 to the no. Nope. Okay. So this, sorry, I know this is right. I just want to understand why. So 100, and then you have 1,000, and then you have 10,000, and then you have 100,000. Okay. So 10 to the 6 is, okay, I get it. For some reason I think the 1 times 10 was like confusing me a little bit. Okay. So this will run 10,000 times. So to check the validity, you say if A times a increment of 0 equals prize of 0 and no, that's incorrect. You would say x equals a times a increment of 0 plus b times b increment of 0, and you'd say y equals, do the same thing but change that to 1. And then if prize, or I guess you could say if xy equals prize, then you're valid. And then for updating, if necessary, you say if a is less than the previous a, and then what do we return? Just the number of tokens, the minimum number of tokens. I mean, I guess you could just calculate tokens here. So you could just say like tokens equals 3a plus b, and then yeah, and then just like update it. Okay, so I could do that, and then so let's code up the brute's force, and then maybe we can optimize somehow with binary search. Maybe I'm not really sure, but I do know that we can, at least for each component, if we do each component separately, we can check if x is greater than or less than or whatever. Okay, so let's do this. So let's code that. So we want to parse inputs and then just do it. I guess I'll just do it all in one function. So f equals open claw contraption test.in as read only, prints f.read. So let me just make sure it's working, and then f.close. Okay, and let's put in some test data here. Oh, what we could do is actually solve for one case. So make a function called what are these? Yeah, so solve claw, or like get min tokens, and it takes in a claw machine. No, it takes in a increment, b increments, and prize, I'll call it. Okay. So first thing I want to do is probably separate this into a list separated by new lines, which will be called clause equals f dot read dot split by new line character. And then let me just see what that does, because there might be a new line tagged at the bottom or something like that. Oh no. So that just splits it. I think that's default behavior. Well, it's empty. It's white. So there's no way I can split it by two new lines, right? Is that possible? Oops. And then if I have another idea. For line in f dot read lines, and then we'll have clause, and then we'll have claw. If line equals just a new line, then we'll say clause dot append claw. Otherwise, claw dot append line dot strip. Let's see what that looks like. 3. All right. Maybe we just say claw dot append. Do we have to reset it? All right, be patient. Okay, so this is the first line. So we want to strip that line. Okay, if it equals empty string. If line dot strip, I guess. If line dot strip equals empty string. Let's say here print empty found, because it looks like we're never appending to claw. Okay, clause. Okay, let's just debug it here. Claw. This is sort of complex input data, so it's okay if this takes a while. Okay, so it seems claw is never... I'm never adding anything to claw here, so... We do say claw.append line.strip, but it does not seem to work. Oh, is it because we make it empty every time? That sounds like it could be it. So we actually want claw outside of here. Still no. And we only actually want that there. Okay. Let's look at the result. Okay, no. So that's once we added the claw. So we added the claw. Oh, this could be interesting actually. So this could be right. So here's one claw, here's another claw, here's another claw. 1, 2, 3. But I only have 3. Why do I only have 3? There should be 4 claws. Is it because the last is the last line? Oh. I mean, yeah, it's because the last one isn't being added, so I'll just say this here and then not Okay, 1, 2, 3, 4. Okay. Alright, so now we have them separated into claws. Alright. Like claw rules basically. Alright, so now what we want to do is extract our relevant information. So I mean we could split it by colon. So let's just do it for one claw. So for rule in claw, rule equals rule dot split at the colon. So let's just see what that looks like. And we only want the second part, to be honest. Well, not necessarily. Okay, so if rule of that equals button A, then, and where are we gonna store all the information? In another list? Well, no, because we only solve it for one of them. So this will be in, yeah, so at the end of this we'll have it. And then, yeah, this would be like for claw and claws. And then at the end of this we'll say, so here we'd say A increment, B increment, and prize. Okay, so now rule. So the second half of rule right now is x plus 69 y plus 23, this string. So we could just read onwards from the last digit or so. Or not the last digit, after the, I mean you could split it by plus sign. No, you can't. Well, you have to split it again actually. So x rule, y rule equals rule 1 dot split. Let me just print those. Wait a minute. Okay. So here is x rule, y rule. So we want x rule from the second character onward, because that will filter out x plus. So, and this will be A increment of 0. A increment of 0, but it's not changeable like that, so we'd have to make it a new tuple. Like this. B increment equals, we don't know anything about that. Oh, maybe we're good. Maybe we could just, so because this is a, so we could just say um, y rule from 2 colon. And the problem with this is, oh no, it's fine. I was gonna say there's an empty space here, but I guess it's fine. Okay, elif rule 0 equals button B, then same thing. I could pick up the pace here a little bit. B increment equals x rule by rule. Elif, if it's prize, then oh, so instead of splitting, no, that's fine. Okay, so now we have same thing actually. So now instead of the equals, so same thing. Now it's just prize equals. And I think you can actually simplify this a lot. So you can always do this for all of them, no matter what. And then you can just say, yeah, you can just take this out of all of them. Alright, so after that, let's print A increment, B increment, and prize. Oh, we have a comma. Wait, what? Where's the comma? Oh, here? And then, so yeah, this one has a comma, I guess. So we can exclude the last character. Can you do it like that? Yeah, okay. So exclude the last character. Alright, now we're good. And we want to map them to integers, of course. We can just do that here or something. So how we I'll just do it here. Okay, there we go. And then we want to get min tokens passing A increment, B increment, and prize. Alright, so for A in range 100, for B in range 100. Then we'll also say like min tokens equals actually I could say -1. Okay, well no. This should be an arbitrary large number. Okay. And then we say x equals A times A increment of 0, the x component, plus B times, yes, plus B times B increment of 0. Y equals A times A increment of 1. plus b times b increment of 1. If xy equals prize, then print viable combination found with a equals, b equals, and put an f right there. Then min tokens equals the minimum between itself and 3 times a plus b. Then print min tokens infinity. That's because it never is valid. So I just returned the. So let's take the context of this problem. The fewest tokens. So I can't set it to 0, unfortunately. But I can say if min tokens equals infinity. So if it's not possible, I guess we could say like, that's probably a weird way to do it. So possible equals false. Then here we can say possible equals true. If not possible, I guess we could say just if possible, return min tokens, else return 0. And then we want to do this for claw in clause. And we'll say total tokens 0 and total tokens plus equals that. Print total tokens 480. All right. All right. Let's try it with the actual input. I guess Control A is exists for a reason. All right. And then we will put it in here and change this to there and try it again. We get this number. Let's try it. Okay, it's correct. But is there another way we can do it that doesn't involve that? So I wonder if it's possible to solve for just one component. So if you have like, what's the example they gave us again? So you know that 94A plus 22B must equal 8400. So 3 of these gives us 66. So like 3 of these cost us 3 tokens. 1 of this costs us 1 token. So can we like rewrite it in terms of tokens? So 3 tokens can get us 94 or 66. 2 tokens can get us exactly 44. 1 token can get us 22. So I'm thinking maybe we can like so this would be our list or whatever that we're binary searching through maybe. Yeah, and then maybe we can this seems pretty complicated, so I think I'm just for now going to leave it at the brute force solution, especially because it's only 10,000. I don't know if there's like a trick or something on how you're supposed to do it, but it's really not that expensive. So yeah, so that was my day 13 Advent of Code solution. The trickiest part of this problem is converting the raw inputs into stuff that you can use. It's not really tricky, it's just kind of time consuming. The problem itself is probably interesting if you go more into it, but I think that's all I'm willing to do for now. I'll look at it again, but yeah, that's everything for today, so thank you for watching.